So we are in the next section. This is Friedel-Crafts acylation. So what's the difference between acylation and alkylation? In the case of alkylation, you have an alkyl group, which is the R group. It could be something like methyl, ethyl, T-butyl, etc. But if you have an acyl group, this is your acyl. So you have a carbonyl group, it's like a keto group, attached to an alkyl group. So that is called an acyl group. Now, just like with alkylation, where you had an R group directly attached to the Cl for alkylation, for acylation, you have the RCO-Cl group, and the catalyst is the same. So the product that's expected here, you break the bond between the Cl and the carbonyl, and the product is this. You get a ketone. So the initial product produced is a ketone. So let's look at, in the next slide, the mechanism for this reaction. So you have the catalyst and the electrophile source. This is the electrophile source and the catalyst. So the initial reaction involves the Cl donating an electron pair to the Lewis acid catalyst. Showing the electron dots around all the other chlorine atoms. And this is a negative. This is a positive, like in the other cases. Now, instead of forming the carbocation, like in the case of the alkylation reaction, this forms an acylium ion. Okay, positive charge is on the carbon. And then the conjugate base of the acid is produced. It's understood that all the chlorine atoms now have their lone pairs, and aluminum gets a negative charge. Now this is our electrophile, and this is called as the acylium ion. Okay. Note the difference between a carbocation and the acylium ion. Acylium ion has a carbonyl group. Now we're going to look at the acylium ion specifically. Okay. So, same as on slide 1829. Okay, so the first part is the same. And I'm on slide 1831. If you look on the bottom, that's where the information will be different. The acylium ion is further stabilized. So you had this, positive. Now, the lone pair from the oxygen can become a pi bond between the carbon and the oxygen. So the acylium ion is resonance stabilized. And it does not allow the carbon with a positive charge to undergo rearrangement. Okay. So the acylium ion does not undergo rearrangement because the positive charge on the carbon is shuttling between the carbon and the oxygen. Now let's look at the entire mechanism. We've shown how the electrophile is produced. So how does the electrophile then undergo reaction with a benzene ring? So the format is going to be very similar to the reactions you've seen before. And the first step is where the electron pair from the pi bond moves to bond with the carbon of the acylium ion. And then this pi bond moves over to the oxygen. So you have the keto group on the other side, and the carbon here gets a positive charge. So you can draw other resonance structures like you've done before. Positive here. This remains the same. And then you can move the pi bond like I've shown. Positive charge here. Okay. So now you have 3 resonance structures. That's your sigma complex. And then the last step, that's the proton transfer step. PT. Now the conjugate base comes along, remember, show lone pairs around one of the chlorine atoms, but all the other chlorine atoms have 3 lone pairs as well. This folds in. I'm going to draw the products up higher. So you have the benzene ring, plus HCl plus your regenerated catalyst. See that? Proton transfer. We go over it again. It's the last structure. This is the conjugate base. The catalyst must be regenerated. So one of the bonding pairs of electrons is used to abstract the hydrogen. This falls back in to produce the the bond inside the benzene ring. And so your products are, of course, the ketone, HCl, and AlCl3. This is a catalyst which is regenerated. So that's the mechanism for the acylation reaction. And this is slide 1832. Okay. Now what about the acylation reaction? There are some alkyl groups, let me adjust this. There are some alkyl groups that cannot be attached to a ring by Friedel-Crafts alkylation reactions. Remember, we saw this being a problem. So if it's alkylation, you can have rearrangements. But with acylation, rearrangements do not take place. So we can produce certain products that cannot be made using the alkylation reaction. And we'll see, you'll understand when I do this example as to what I'm talking about. Now, if I used the benzene ring, I'm going to put a circle in the center, and if I wanted to make an alkylation product, okay, this is butyl benzene, and we've tried this before. You may want to go back under the alkylation section and see what happened when we tried to make butyl benzene. We did not get butyl benzene as the major product. We obtained butyl benzene as the minor product when we tried using chlorobutane in the presence of aluminum chloride. Look at the alkylation section. Okay, so this was not the major product. But, okay, this is not the major product. When we use this reaction. But if we went the roundabout way and started out with this reactant, you still have 4 carbons, but the carbon that is connected to the Cl is a carbonyl carbon. So the first time around, you get a ketone. Okay, get a ketone. And then to make the butyl benzene, see that? This group must undergo reduction. You have a hydrogen and a hydrogen. See that? The carbonyl group must be reduced. And the method for reducing the carbonyl attached to the benzene ring, you see that? It's not any carbonyl. This is attached to the phenyl group, attached to the benzene ring. So this is a specific type of reduction. If you need to reduce this carbonyl, it is done through Clemmensen reduction. So what is this? This is done using amalgam. Amalgam is mixing zinc with mercury. That's zinc amalgam. They have used amalgams in the past for filling teeth. They don't do that anymore, but any metal mixed with zinc in a certain way is called amalgam. And of course you need some other reagents, HCl and heat. We've seen reducing agents such as zinc or Fe with HCl, but the Clemmensen reduction, remember, uses zinc amalgam in the presence of HCl and slightly higher temperatures. So this is a good alternative reaction for making butyl benzene. So butyl benzene is produced as the major product. In this particular case, it says that they get about 73%, and which is a very good yield for organic reactions in general. So instead of doing it in one step and not getting a large quantity of the butyl benzene, if you did acylation first and then reduced it, then you can get more of the butyl benzene, or more of the non-rearranged product. What else is there to see about acylation? Remember, in the case of alkylation, polyalkylation was a problem. Okay. Next slide. unlike polyacylation, unlike something missing here, unlike alkylation. Okay, unlike alkylation, polyacylation is generally not observed. So with alkylation, polyalkylation occurred, and that was a problem. Here, the benzene ring reacts to give the ketone, and then no further reaction takes place. Even if you had excess of the acyl chloride, no further acylation occurred. So polyacylation was avoided, which is a good thing because you expect to produce a simple ketone, and that's what you get. So that ends the reactions to produce the monosubstituted benzene compounds. So the first one we saw was bromination, then chlorination, nitration, sulfonation, alkylation, and acylation.